In this video, we are going to be doing the graphs of sine and cosine functions with transformations. So we start out with a unit circle. Now remember that it is x squared plus y squared is equal to 1 squared, or just 1. That's a circle centered at the origin with a radius of 1. If we define sine alpha as being y over r, then on the unit circle it's just y. And similarly, cosine is x over r on the unit circle, because r is 1, it's just x. And we get this equivalencies if we're on the unit circle. For the tangent as being y over x, cotangent is x over y, secant is 1 over x, and cosecant is 1 over y. Now, we can now take our unit circle and turn it into a function in which the input would be the angle, and the output would be the x value or the y value on the unit circle. So we're going to start writing these in terms of, excuse me, as the function in which my input or my x, my argument, is an angle in radians. And it always has to be in radians. And then my output of the function will be whatever I'm looking for on terms of the unit circle. So we can now start doing the graphing. Before we start graphing, let's talk a little bit about periodic functions. We say a function is periodically if it has a non-zero constant, so that when I put in that non-zero constant into my domain and I add it to my original f function, then I get the exact same output out by just a matter of a constant. We call that a periodic function. Sine, cosine, secant, cosecant all have a period of 2 pi. That's how long it takes us to get back to where we started. Let's actually look at the unit circle and go through that. So if I think of that, this is the angle of pi over 6. Here's my output of 1/2. The next time I have an output, so if I'm looking at the sine of pi over 6, is an output of 1/2. The next time I get an output of 1/2 is right here. So I have gone a distance from this angle to this angle, not quite pi, and in fact this angle is 5 pi over 6. So in other words, the total angle is 5 pi over 6, but this angle between them is 4 pi over 6. So let's see if I add another 4 pi over 6, if I get the exact same output. Well, if I add another 4 pi over 6 from this ending point, I get this. I don't have the same output. So I know that my period here is not going to be pi over 6 or 4 pi over 6. So the next time I get a positive 1/2 as the output, so as I look along the unit circle, I'm looking for a positive 1/2 for the output for y, so the y value. I get it here, but we know that I can't consistently add that 4 pi over 6 and get the same one. That's negative. That's negative. Oh, so it takes a full rotation to get back to the same output value consistently. And so that's how come the sine of alpha, same thing with cosine of alpha, and their reciprocal functions, so the CSC, the cosecant, and the secant of alpha, the reciprocal functions, have period of 2 pi. Because that's how long it takes for us to get back to the exact same output consistently. If I add 2 pi to pi over 6, I'll get the same output. Similarly, if I'm looking at this angle, which we know is 2 pi over 3, if I wanted to get the exact same output as square root of 3 over 2, consistently I have to do one full rotation to get back to that. And so sine, cosine, cosecant, secant has period of 2 pi. Tangents, however, have periods of pi. That's how long it takes to get from consistently the same output when I add that constant to my angles. Now, again, what we have is we know that the arc length is alpha times r, alpha being the angle. We're in radians. You know you have to be in radians. So the arc length s is just alpha because we're on the unit circle. R is 1. So that means that when I go ahead and graph my function, where s, or sine of alpha, I can just think of it as the sine of my arc length, and I end up with x f of x is just x sine x. What the heck does that mean? Well, what that means is if I take my angle and I do y is equal to the sine of my angle, here's my ordered pairs. And you can see that when I have pi over 6, here's the angle pi over 6, it translates to a point on the graph, pi over 6 with an output of 1/2. I put in pi over 4. Here's pi over 4. It translates to this point, which is pi over 4, which isn't listed here, is square root of 2 over 2. So this translates to square root of 2 over 2. Then I continue on, and you can see this is what the sine wave ends up doing. As I go around the unit circle and I compare these points here, and I transfer these points straight across, you end up with this graph right here. So this is the sine wave. And we see this is one period because it takes one full rotation, which is 2 pi. So the fundamental cycle, or how long it takes to get every possible output for the sine wave, is the period, and that is the distance from beginning to end is 2 pi. So this is the distance of 2 pi. Now, because of the fact that this goes on forever unless I restrict my domain, this is the sine wave, where this blue part is the fundamental cycle, which has a length of the period of 2 pi. For sine, we have 5 key points. We choose key points that are easy to graph, so we choose the 0, 0. We choose pi over 2, 1. We choose pi 0, 3 pi over 2, negative 1, and of course 2 pi 0. Now, could I have chosen these as well? Sure, I could have chosen these as well, but it's easier to take the key points and transform them, having outputs of 1 versus outputs of 1/2. You could have used any of them, but typically our 5 key points, again, are these here for sine. So doing the same thing with cosine, here's my cosine wave, and here's the fundamental cycle of the cosine wave. It also has the ability to continue on in both directions each way. And again, this part of the graph in blue is the fundamental cycle. This is continuing to the left. This is continuing to the right. I'm gonna stop just a moment and just talk a little bit about where I am in terms of quadrants. Now, if I look at my unit circle, I'm gonna go back up here to my unit circle. Notice that this is quadrant 1. So this is quadrant 1. Here is quadrant 2. So from pi halves to pi is quadrant 2. So continuing on, we know for all of them, this is quadrant 1 outputs. This is quadrant 2 outputs. This is quadrant 3 outputs. And of course, this one being the last one, quadrant 4 outputs. If I go to the left of the line of the y-axis, then this is quadrant 4, but I'm going in a negative rotation. And this is really important, especially when we do inverses. So that means on my unit circle, I have gone in this rotation because my angles are negative. So negative pi over 2. I'm in quadrant 4. So this is negative pi over 2. Similarly, this is quadrant 3. This is quadrant 2. And this first one is quadrant 4. But on the left side, quadrant 1, on the left side of the y-axis, we have negative angles. So we're going in a negative rotation. So negative rotation, negative rotation, negative rotation. So if you see anything on the left side, it is quadrants 1, 2, 3, 4, but they are negative rotation. And you'll notice that each time we do these rotations, I go back to quadrant 1. The next one is quadrant 2. The next one is quadrant 3. And my final one is, of course, quadrant 4. So if we're going in this, we are going with a positive rotation. If we are going in this direction, we're going in a negative rotation. So I just want to stop and say that's true for all of my trig functions. And also I want to remind you, because it'll come up, about odd and even. So if we go back to how we define odd and even, back in terms of the pre-calculus 1, we say if we put in a negative x and we get the exact same function, we know this is an even function. We also know that we have symmetry with respect to the y-axis. So it's symmetry with respect to the y-axis. And similarly, f of negative x, we put that in there and we get the exact opposite we start out with. This is odd, and we have symmetry with respect to the origin. So just as a reminder, and if I take a look at my sine wave, coming back up here, I can see my sine wave. I can see my sine wave up here has that symmetry with respect to the origin. You can see this point is this point. So sine is an odd function, and so is its reciprocal. Now let's just go back to cosine because we were there before I sidetracked. Cosine, same kind of thing. I take the points and I put in 0, 1 comes out. I put in pi over 3, 1/2. We use the key points of 0, 1, 1 pi over 2, 0, pi negative 1, 3 pi over 2, 0, and 2 pi 1. Same thing, quadrants 1, 2, 3, 4. What we can see though, when we look at a larger graph and not just the fundamental cycle, is that this cosine wave has symmetry with respect to the y-axis. So cosine of x is even, and then of course what we'll find out is its reciprocal, which is the cosecant of x, is also even. Okay, so here's my key points, just like I talked about. Here's my key points. So when we talk about transformations and I ask you for the key points, I'm asking for where those key points went to. The other thing when we talk about sine and cosine functions is that they have amplitude. The amplitude, the way that we describe amplitude, is the distance from the baseline to a maxima, or the distance from the baseline it is to a minima. To find the total distance traveled is you would take the amplitude and multiply it by 2. If you know the total distance traveled, then you can find the amplitude by taking the maximum, subtracting off the minimum, and dividing by 2, and that will give you the amplitude. Again, the baseline for our sine and cosine waves without transformation is the x-axis. So the only functions that have amplitudes, by the way that we define amplitude, is sine and cosine. They're the only ones that have amplitude because as a maxima to a minima. So, and of course, we know that the ones that have periods of 2 pi are sine, cosine, secant, cosecant. The periods that have pi are tangent and cotangent, which we will do in the next video. Let's talk about some characteristics about the cosine function and also with the sine function. Is that the sine and cosine, they both have period of 2 pi, that both have a domain of negative infinity to infinity. But note the domains that we put in, our values that we put in are angles. So we don't put in angles that are in degrees, they have to be in radians because radians then turn into arc lengths and arc lengths are real numbers. So we always put in, whenever we are wanting to graph, we always put in our x is going to be a real number. But it's also, if we're talking about an angle, the angle has to be in radians. So you can't graph on the xy plane as a sine or cosine wave unless your angle is a radian measurement. Now I'm going to deviate just a little bit in terms of how it's described in the book, and the way I describe it is I want to go back to the way that we did this back in Precalculus 1, where we have the a, we have our function, and then we have this number. We're going to call this omega now. And then x minus phi, we would have called that c, and then we had done the plus d. So what we would have seen in Precalc 1 is we would have seen something like this. My f function is given, and then my transforms function g of x is equal to, this is how we would have done Precalc, a f of, and then I would have done b, and then you would have seen x minus c, and then plus d. Now everything that happened before in terms of transformations are still going to happen. Our a in front in Precalc 1, we still call it a, that is our amplitude. That is the distance traveled from the baseline to a maxima or a minima. And remember, the only ones that have amplitude are sine and cosine. We call omega, which we would have normally have called just the b value. That is our horizontal shrink or stretch. Our phase shift, which is phi, that's this. We would call it c before, but now we're calling it phi. That's called a phase shift, and we're moving it just left and right. And this B, which we would have called in pre-calc 1, would have been D, and that would have been our vertical translation up or down. Now the period, whatever the period is going to be equal to that, whatever, like 2 pi or pi, and divide it by omega. So as an example, if I would have had the sine of 3x, this is my function, f of x is equal to, my period P is going to be the period for sine, which is 2 pi, and then divided by my period change, which is omega, so that's 3. And so that's my new period. That tells me the length from beginning to end. So just a little side note. As an example here, let's take a look at 3 different graphs. The first one's just the sine wave. That's the one here in orange. We notice that the sine of 2x is a vertical compression, so what we learned before is still true. So notice that my original orange goes from 0 to 2 pi, but by making it sine 2x, it is a horizontal compression, so it is half the length, so its period goes from 0 to pi. If I have the sine of x over 2, that is a vertical stretch by a factor of 2. Remember, it's the opposite. And so for me to do a full cycle, I'm actually going to have to end out way out here at 4 pi. So let's go ahead and take a look at our first example, and they're asking us to sketch at least one cycle, label the 5 key points for one cycle. So let's talk about what this negative does. What the negative does is just do a reflection across the x-axis. So what we learned before in pre-calc 1 in terms of transformations of graphs still holds true here. So I'm still going to start, my period is still going to go from 0, I'm still going to end at 2 pi. So my period does not change. My period is 2 pi divided by my omega. In this case, my omega is 1, so I just have 2 pi divided by 1, which is still just 2 pi. Now, I know that my key points should be 0, 0. I normally, so here's my key points. So let me just list my key points. It should have been 0, 0. These are my key points. And then it would have been pi over 2, comma 1. And then it would have been pi, comma 0. And then 3 pi over 2, comma negative 1. And then my last key point should have been 2 pi and 0. What this does is it takes all of my y values and multiplies by a negative 1. So it's still going to be 0 out input, still pi over 2 input, pi input, 3 pi over 2 input, and 2 pi input. So those don't change. What changes is the output, and so this goes to still 0, this goes to negative 1, 0, 1, and then 0 again. So this is my transformed graph. So I'm going to go, instead of into a maximum, I'm going to go into a minimum, then at 0, and then I'm going to go to a maximum, and then I'm going to go back. So this is one cycle. And this is where my key points went to. Let's take a look at the next example. So again, I'm going to go ahead and draw my key point, or write my key points. So key points. My key points are 0, 0, pi over 2, comma 1, pi, comma 0, 3 pi over 2, comma negative 1, and then of course I have 2 pi, comma 0. What this does is it does a vertical shift. It's a phase shift, right? It's a horizontal, not vertical, horizontal phase shift. It takes my graph and it goes in the opposite direction, so it actually, my phase shift is right, or excuse me, left. I want to go left, left, pi over 2. So that takes all my key points and goes left. So I still have the output of 0, still have the output of 1 and 0 and negative 1 and 0. But now this is going to go to negative pi halves. This is going to go to 0. This is going to go to pi halves. This is going to go to pi, and this is going to go to 3 pi over 2. So I still have a omega of 1, which means my total cycle from beginning to end is a length of 2 pi. I start at negative pi halves. I end at 3 pi over 2. So my point is here, and then here, then here, and then back. So here are all of my key points graphed, and all I've done is a phase shift left pi over 2. My next example has a lot of things going on, so I'm going to start again with my key points. and it is a cosine wave. My cosine wave key points is 0, 1, 0, 1, and then pi over 2, 0, and then 3 pi, pi, man, I want to just jump to the end. So pi, negative 1, 3 pi over 2, 0, and then of course we're back to 2 pi, 1. Okay, let's talk about what each piece does. This is a phase shift, so this is going to go right, and I usually do that first. I'm going to go right pi over 3. So I'm going to add pi thirds to each one of those. This is an amplitude change, so it takes all my y values and it reflects it. So I'm going to reflect over the x-axis, and I'm going to stretch by 3. So my amplitude is 3 times as high. And then my last piece here is I'm going to move it down 1. So down 1. So let's go ahead and do this step by step. And so let's do our first one, which is all of my x's are going to add pi thirds to it. So I'm going to go ahead and still have 1, still have 0, still have negative 1, still have 0, still have 1 as my outputs. But this is going to go to pi thirds. The next point should go to 5 pi over 6. The next point should go to 4 pi over 3. Check my math on this. The next one is 11 pi over 6. And then my last one is 7 pi over 3. Okay, so that takes care of the phase shift. I also need to take all of my y values now and multiply them by a negative 1. Now that my inputs, pi thirds, 5 pi over 6, 4 pi over 3, 11 pi over 6, and 7 pi over 3 have stabled. Then we are now going to multiply all of my y's by negative 3. So it goes to negative 3, and then 0, and then positive 3, then 0, then negative 3. And then my last step is I'm going to move them all down 1. And so to save time, we know this is going to go to negative 4. This is going to go to negative 1. This is going to go to 2. This goes to negative 1, and this goes to negative 4. Okay, so let's graph this. So we start out with the point pi thirds, and we're going to go down to negative 4. So there's that one. And then I'm going to go to the end. The end point should be 7 pi over 3 and pi, or negative 4. And the reason I do that is this is my check to make sure I've done my adjustments right. If I take 7 pi over 3 and I subtract off my starting point, which is pi over 3, then that tells me I should end up with 6 pi over 3, which still is 2 pi. And I expected that because my omega is still 1. So that's correct. I've got that part. Now, my halfway mark is going to be this one, should be 4 pi over 3. So my halfway mark is 4 pi over 3. Let's talk about the baseline. The baseline has moved down 1, so let me just go ahead and put my baseline here. The other two examples, my baseline did not move. So my baseline moved on this one, and you can see the distance traveled from the baseline to a minimum, or the baseline to a maximum, is a distance of 3. Now, instead of going from the baseline and starting in a maximum because it's a negative, I start in a minimum. I find my other quarter marks, which is this one, 5 pi over 6, and it should be 0, but it went down to negative 1, so 5 pi over 6, negative 1 is right there. And my other one is 11 pi over 6, negative 1, which should be right here. So here's what my sine or cosine wave looks like with the transformations. Okay. So it had a baseline move, unlike the other ones, and it had a reflection across the x-axis. We did have that one on the first example. But this also had a phase shift, and it had an amplitude stretch. Okay, we're just going to quickly do this. Let's do this one. I'm going to talk about this one, though. All this does is it changes my period from 2 pi divides it by 3. That tells me that I'm going to start at 0. I'm going to end at 2 pi divided by 3, which is right here. My halfway mark would be here. My quarter mark would be up 1, and my 3/4 mark would be down 1, and so it looked like this. Okay, that's just quick, very quick. That's what it looked like. You should confirm that with your points. I want to talk about this one too. This too does a compression, and this pi means that it goes to the right. So I would start at pi, because it is a right movement, and my total distance traveled is just going to be pi. So from beginning to end is going to be my period of 2 pi divided by omega, which is 2, so it's going to be pi. So this is where it would end. And then I would have my halfway mark, my quarter mark, my 3/4 mark, and so here's my sine wave. And you really should confirm this with your own key points to make sure that you're understanding where I'm getting mine. Okay, now actually I did want to get down to this one here without making this a super long example. With this one, we need to get the phase shift isolated to get the omega isolated so we can get the true phase shift. So let's rewrite this as -1/2 the cosine of. Now I'm going to factor out a 3 off of that. So then when I factor out a 3, in other words, I'm dividing by 3, it is -pi/6. So make sure if you have one like this on the homework that you factor off that omega to get the correct phase shift, because if you don't, you won't get the correct phase shift. Now, this tells me I'm going to go right pi/6. This tells me that my period, which should be 2 pi, is going to be divided by 3, so my total distance traveled from beginning to end is 2 pi/3. This tells me I'm going to compress by 1/2, and it's going to be a reflection. Very, very quickly, let's just draw the graph, not doing all the key points because I did it up above on the previous ones. And you really should do that yourself to make sure you've got those key points down. Now what I know is that it is going to start at pi/6. So if that's pi halves, so about right here is 1/6. So I move over 1/6, so that's pi/6. I need to end at 3 pi/2 plus 1/6, so that's about right there. That's my ending point. This is a distance of 3 pi/2. That is how far my graph should be. And I don't have any, my baseline does not change. My amplitude does compress. If this is 1, then I'm going to come in at about 1/2 is right here. And then I'm going to end at 1/2, -1/2, which is going to be right here. My halfway mark is about here, so it's going to look something like this. It's going to be half as tall as I normally do, and you really should check your key points, but that's basically the graph. Now let's take a look at these where we're asked to build the equation based on this information. So we have the sine wave. It is shifted pi halves to the left and reflected over the x-axis. So the negative gives me a reflection. There's my sine. It doesn't say anything about a period change, so now my omega is 1. So then in the inside, to make it go left, I'm going to do x plus pi halves. So this is my function for that transformation. When I look at the cosine, I need to go down. I have a pi thirds to the right, and it is stretched. And since it doesn't say it is a period change, we know that that stretch must be the amplitude. So this one is going to be f of x, my amplitude of 4. The cosine, it says nothing about the period, so we assume omega is 1, so it'll be x. I want to go to the right, so it's going to be minus pi thirds, and then I need to go down 2 units, so minus 2. Now again, this next and final example of this kind is it's the sine. It is going up, it's going to the right, and it is shrunk. We make the assumption, unless it says that this is a period change, it's going to be y is equal to f of x, which is going to be 1/2. The sine of x, we want to go to the right, so it is going to be minus pi sevenths, and we want to go up 3, so plus 3. That moves the baseline up 3. If I'm given a graph and they're asking me to find the sine or cosine wave that matches that graph. In this case, I'm asked for the sine wave that matches this graph. The first thing I'm going to do is determine the amplitude. The way that I determine the amplitude is this is going to be the max minus the min divided by 2. Now these are the y values, so I can tell you the amplitude. And then my baseline is going to be the distance of the amplitude from a max or a min. So in this case, my max is -1, and then I'm going to subtract off. My min is -5 divided by 2. So my amplitude is -1 plus 5 divided by 2, which is an amplitude of 2. So from my max or min, I go a distance of 2. So here's my baseline. That baseline trends to the fact that I need to do a -3 to the outside of my sine wave. So that is the -3. The fact that I have this amplitude of 2, that tells me that that multiplier in front has to be 2. This is the b value based on the fact that I am using that y is equal to the sine, y is equal to a, the sine of omega x minus phi plus b. So I found the b, I found the a. Now, normally I would start at 0, 0, and I'm still starting at 0, but I'm not starting at 0, 0. I'm starting at 0, -3, and that's taken care of by this part. I have the fact that I should go into a total period of 0 to 2 pi. The distance traveled for my sine wave for one period here happens to be 4. That's going to tell me what my omega is. So my omega, 2 pi divided by omega, must be equal to 4, because that's the distance I traveled from beginning to end. That tells me my omega, or my phase shift, must be pi over 2. So, not my phase shift, I don't have a phase shift. My period change, my omega is pi over 2. So to bring this all together, I have y is equal to 2. That comes from here. The sine of pi over 2 x, and then my baseline has to be moved down 3, so then -3. And so that is the graph that describes, that is the function that describes that graph. Now let's take a look at my cosine wave. This is, they're asking you for a cosine wave. The cosine wave here, I'm going to do the same kind of thing. Now I could start it here. I could start it here, but remember cosine starts in a max or a minimum. I could start it here if I wanted to. I can start it anywhere. I always start it for the least amount of work possible. So I'm going to start my cosine wave being right here, and I'm going to have it end right there. So I know right out of the gate that 2 pi divided by omega must be the distance from peak to peak, which happens to be pi. That tells me right out of the gate that my omega must be 2. So I know what my omega is. I have a compression of 1/2, so my omega has to be 2. Now I'm going to find my amplitude. So my amplitude is going to be the max minus the min divided by 2. So this is 2 minus a -4 divided by 2. So I have 6 divided by 2, so my amplitude is 3. My baseline, I'm going to go from a min or a max and count down 3. 1, 2, 3. My baseline has moved to here. That tells me my baseline is at the line y is equal to -1. That means I have shifted down 1. So let's bring this all together. Using the fact that I have cosine, so f of x is equal to my amplitude, which is 3, the cosine of my period, which is 2, and x, and then my baseline -1. And so that describes that graph. Last example here, we are looking at an application. A weight hanging on a vertical spring is set in motion with an upward velocity of 4 centimeters from its equilibrium position. So let's just draw what we have. So that's my spring, here's my weight. So the weight, and it's going with an upward velocity of 4 centimeters per second from its equilibrium position. A formula that gives the location of the weight in centimeters as a function of time t is given as this. So if I were to graph that, it's going to describe the motion that this makes as it goes toward and then down, and then toward and then down. So this would be something about what it would look like, right? Assuming, of course, that it's not going to have any issues for slowing down. It's not going to have real life issues of slowing down as the spring, goes to rest. So we assume there's no dampening motion. We want to know the period of the function and sketch this interval from 0 to 4. So I know it's going to look something like this. And I want to know the period. Well, the period has to do with the omega there. My omega is pi. That tells me my period is going to be 2 pi divided by omega, which is 2 pi divided by by pi. So my period is 2. That means my graph is going to look something like this, right? Assuming that the upward and downward motion is the same distance. Let's just pretend that this amplitude is the same in both directions, that my drawing is that good. My amplitude, of course, is the negative pi force, so that when I start doing the motion, I would actually be starting right about here. This would be my start, because I need to go first in a negative. And so that would be my start of my graph, which is right here. And then here would be the halfway mark, and then after 2 seconds, I would be right there. So at 2 seconds, I was there, and then at 4 seconds, I'd be there. Now, I want to just talk about this. When we're talking about a spring, by the way, this motion is negative, this motion is positive. That's why even though the graph, if I were to graph this over time, would look like this, it would oscillate back and forth, up and down like that. In terms of the graph of the sine wave, we actually start here in a downward, because up means negative, down means positive. Don't ask me, go ask your physicist. Anyways, there it is, 6.1.